On July 1, 2025, astronomers flagged 3I Atlas as the third confirmed interstellar visitor. But within months, it defied every expectation with 14 unexplained anomalies, a mysterious anti-tail, and a course change that rewrote its story entirely. Quietly, nearly every major space agency shifted from lab tests to the largest planetary defense drill in history, all centered on this one object. If 3I Atlas is just a weird comet, why did the world's response escalate so far, so fast? And what do officials suspect that they aren't saying? The official story says there's nothing to see. But the actions behind the scenes reveal a global scramble that starts with hard data and leads somewhere nobody wants to admit. So what really began when the sky changed? The first confirmed sighting of 3I Atlas came just after midnight on July 1, 2025. The Atlas telescope in Chile picked up a faint, fast-moving object on its automated sky survey. Within days, astronomers around the world were tracking its path, running calculations and comparing notes. The numbers did not fit any pattern familiar from the thousands of comets and asteroids cataloged in our solar system. The object was on a hyperbolic trajectory with an eccentricity of 6.14, far beyond the limit for anything bound by the sun's gravity. Its speed sealed the case for an interstellar origin. At discovery, 3I Atlas was traveling 221,000 kilometers per hour. That's about 137,000 miles per hour. As it approached the sun, that velocity would climb to a peak of 246,000 kilometers per hour, more than 150,000 miles per hour, faster than any spacecraft ever built by humans. The Atlas survey team, following international naming conventions, designated it as the third confirmed interstellar object. 3I stands for the third interstellar object, and Atlas names the instrument that found it. Only two other objects, Oumuamua in 2017 and Borisov in 2019, had ever received this label. Each had challenged astronomers in its own way, but 3I Atlas immediately stood out for its size, activity, and the sheer volume of data it began to generate. Observations from NASA's Hubble Space Telescope on August 20, 2025, gave the first reliable estimate of its size. The nucleus was at least 440 meters across and possibly as large as 5.6 kilometers, putting it somewhere between a city block and a small mountain. That made it several times larger than Oumuamua and at least as large as Borisov. The object was visibly active, with a cloud of gas and dust forming around the icy nucleus as it neared the sun. Multiple jets of material were detected streaming from the surface, hinting at complex internal processes and a volatile composition. The object's brightness peaked near perihelion, its closest point to the sun, on October 30, 2025. Its coma grew more pronounced, and astronomers noted rapid changes in both brightness and structure. The spin period was measured at just over 16 hours, with a like curve amplitude indicating a non-spherical, possibly elongated shape. Photometric and spectroscopic campaigns from ground-based telescopes and space observatories captured a flood of data. Teams in Hawaii, California, Egypt, and Chile all contributed to a growing international dataset. By December, 3I Atlas was on track for its closest approach to Earth, about 270 million kilometers away, or 1.8 times the distance from Earth to the Sun. At that range, it posed no direct threat to the planet, but its interstellar trajectory and high velocity made it a rare and valuable target for scientific study. The object's passage through the inner solar system offered an unprecedented chance to observe material from beyond the Sun's sphere of influence, possibly even from another planetary system entirely. With every new observation, 3I Atlas drew more attention from astronomers, planetary defense planners, and space agencies. Its physical characteristics, the icy nucleus, active jets, hyperbolic speed, were all measurable and verifiable. But as data poured in, small discrepancies began to surface. The numbers didn't always add up. The object's behavior, while broadly comet-like, refused to fit neatly into established models. What began as a routine cataloging exercise soon became a global scientific event. The baseline facts were clear. 3I Atlas was big, fast, and from beyond our solar system. Everything else, as it turned out, would be up for debate. Across 4 months, the data on 3I Atlas began to defy simple explanation. In mid-August, the Kotamia Observatory in Egypt measured a dust-to-gas ratio of just 0.05, almost an order of magnitude lower than any comet observed in the last 20 years. That same week, Palomar's 200-inch telescope reported nickel vapor in the coma, but no detectable iron. That composition, effectively infinite nickel to iron, puzzled spectroscopists because even the most metal-rich solar system comets never show pure nickel signatures without iron. Nickel stood out in a way that made no easy sense. By late August, the Apache Point Observatory in New Mexico logged a coma composition dominated by carbon dioxide. Their readings showed a 7.6 to 1 ratio of carbon dioxide to water, the highest ever recorded. Most comets are water ice with a dash of carbon dioxide. 3-1 ATL ACE flipped that script. Meanwhile, a team at Gemini North in Hawaii caught the first images of a sunward antitail, an optical feature where dust appears to stream toward the sun, not away from it. This antitail persisted for weeks, even as the main tail lengthened in the opposite direction, raising questions about the dynamics at play. On September 6th, the European Southern Observatory's La Silla facility measured extreme negative polarization in the dust, with values plunging beyond known cometary ranges. Negative polarization is common in comets, but the degree seen here was unprecedented. Just days later, the SETI Institute's Allen Array detected erratic non-gravitational acceleration. The object's velocity fluctuated in ways that standard outgassing models couldn't fully account for, even after factoring in the jets mapped by Hubble and the James Webb Space Telescope. In mid-September, the Kiso Observatory in Japan reported multiple jets erupting from opposite sides of the nucleus, sometimes simultaneously and sometimes in rapid sequence. The pattern suggested either a highly active rotating core or a more complex internal structure. On September 22nd, the Lowell Observatory in Arizona tracked a sudden brightening event, with its magnitude jumping by nearly half a point in under 6 hours. No corresponding outburst or fragmentation was visible, leaving the cause unclear. October's approach to perihelion brought more surprises. On October 2nd, a team from the Max Planck Institute in Chile recorded a shift in the object's spin period, dropping from 16.2 hours to 15.8 hours over just 12 days. Such rapid spin changes are rare and usually linked to violent outgassing or fragmentation, but neither was conclusively observed. On October 15th, the Lick Observatory in California documented a cluster of smaller bodies moving in tight formation with the main nucleus possibly fragments, possibly a swarm. Their trajectories were so closely aligned that the team described them as coherent within the resolution limit. As perihelion neared on October 30th, the antitail brightened dramatically. The SOHO spacecraft's coronagraphs captured jets firing almost directly sunward, while ground-based teams in Spain and South Africa measured a spike in carbon dioxide emission. The nucleus temperature, inferred from the infrared spectrum, rose to levels that should have vaporized most surface ices. Yet the object remained intact. Perihelion brought results that did not match simple expectations. Early November saw the return of non-gravitational acceleration, this time with a measurable lateral component. The Minor Planet Center's published orbit solutions began to diverge, with the errors growing larger by the week. On November 9th, the Keck Observatory in Hawaii detected a brief outflow of ionized nickel, a feature never before confirmed in an interstellar object. By late November, the growing list of anomalies painted a picture of an object that was not behaving like any comet we had ever seen. The data was solid, but the conclusion was baffling. The scientific community was facing a true unknown, and behind closed doors, the conversation was already changing. But soon, that one oddity grew into a list of 14 distinct, head-scratching features. We're talking ultra-low dust levels, pure nickel vapor, an atmosphere dominated by carbon dioxide, and a persistent antitail that defied easy explanation. The list went on: unprecedented negative polarization, erratic acceleration, multi-jet activity, and sudden, dramatic brightenings. Then came the rapid spin changes, a possible swarm geometry, a flare-up of the antitail as it neared the sun, and a nucleus temperature far hotter than expected. Add to that lateral acceleration and an outflow of ionized nickel. Each discovery was logged, time-stamped, and debated across a flurry of scientific papers and internal memos. The problem was no single theory could explain everything. The mystery wasn't just about one strange comet anymore. It was about a pattern of behavior that broke every standard model we had. For the global research community, the question shifted. It wasn't just, what is 3I Atlas? It became, how could so many anomalies stack up in a single, fleeting visitor from the stars? October 30th, 2025 marked a turning point. As 3I Atlas swept behind the Sun, orbital tracking teams noticed a subtle but undeniable change in its path. Its outbound trajectory no longer matched the predictions based on solar gravity and normal outgassing. Instead of heading out on a clean hyperbolic arc, the new data suggested it was maneuvering toward the edge of Jupiter's Hillsphera, vast region where the planet's gravity can capture passing objects. The numbers pointed to a move that would let 3I Atlas linger in our solar system, rather than racing straight back into interstellar space. This sudden shift reignited the debate among astronomers. Harvard astrophysicist Avi Loeb quickly published a paper proposing a model that could tie several of the object's oddities together. According to Loeb, the persistent anti-tail, usually just a trick of perspective, might actually be a cloud of smaller, compact bodies traveling in formation, not just dust or gas. If 3I Atlas was a swarm rather than a single object, its collective motion could explain the anti-tail's brightness and orientation. More importantly, Loeb's model made a clear, testable prediction. The smaller, less massive members of the swarm should lag behind the main body by tens of thousands of kilometers, especially after passing the Sun. This lag would appear as a faint extension pointing toward the Sun in high-resolution images, separate from the main tail. But not everyone was convinced. Dr. Karen Meach, a leading comet expert at the University of Hawaii, countered that outgassing alone, especially from multiple jets, could create complex, shifting dust features and the observed non-gravitational accelerations. She pointed to past comets that had shown wild jets and anti-tails, arguing that while 3I Atlas was extreme, its behavior still fell within the known range of cometary phenomena. She urged for more precise imaging and observations across different wavelengths before jumping to any exotic conclusions. Throughout November and early December, telescopes from Mauna Kea to La Silla hunted for this predicted lag. On December 3rd, a team at the European Southern Observatory made a stunning announcement. They had imaged a faint sunward structure extending nearly 40,000 kilometers ahead of the nucleus, perfectly consistent with Loeb's swarm prediction. Other teams reported similar features, but some scientists urged caution, pointing out that solar wind effects or complex dust dynamics could potentially mimic the same geometry. These caveats meant that full, undeniable confirmation remained just out of reach. The debate wasn't just academic. It had serious implications for planetary defense planners. If 3I Atlas was a swarm, every aspect of detection and potential interception would need to be completely rethought. For now, the object's behavior remained just testable enough to keep both camps, the comet camp and the swarm camp, scrambling for the next piece of the puzzle. A single object hurtling through the solar system is one thing. A suspected swarm moving at interstellar speeds and behaving unpredictably is something else entirely. As the list of anomalies surrounding 3I Atlas grew, our usual methods for tracking near-Earth objects started to look dangerously inadequate. Radar signals from Goldstone and Arecibo flickered with inconsistencies. Optical telescopes strained to resolve the faint sunward structures that the swarm hypothesis predicted. The software we built to track lone comets kept flagging outliers and possible fragments, forcing analysts to rewrite detection protocols on the fly. The pressure mounted on international planetary defense networks. On November 25th, the International Asteroid Warning Network, or IAWN, issued a rare global alert. All member agencies were instructed to synchronize their observations and submit real-time tracking data for a new, extended exercise window. The official drill was set to run from November 27th through January 27th, 2026. Publicly, this was just the 8th coordinated exercise since 2017, but unofficially, its scale and urgency surpassed anything that had come before. Within hours, the European Space Agency activated its entire planetary defense triad. Mission control, rapid response modeling teams, and ground-based observers worked around the clock for 3 solid days. Internal documents later revealed a multi-billion euro budget surge was approved in less than 2 weeks to expand sensor coverage and data integration. The U.S. Space Force, which had planned its next orbital tracking rehearsal for late 2026, quietly moved up the timeline. They deployed new high-altitude assets and issued a fast-track procurement notice for next-generation tracking platforms. Japan's space agency initiated a national asteroid impact coordination drill, bringing together military, civilian, and commercial satellite operators for the first time under a single, unified scenario. Even countries with smaller space programs like Australia, South Korea, and Brazil joined the exercise, each focusing on tracking high-velocity, non-gravitationally accelerated objects. A new clause appeared in the IAWN drill documentation that raised a few eyebrows. It stated that for the duration of the exercise, classified sensor data could be temporarily integrated into the global feed, but only for objects on non-standard hyperbolic trajectories. Transparency advocates were concerned, but officials argued that the complexity of the 3ITLAS case demanded every available tool. For 2 months, Planetary defense shifted from a theoretical tabletop scenario to a real-time, distributed rehearsal. It wasn't just testing hardware. It was testing the willingness of global agencies to cooperate when faced with something that simply refused to fit the old playbook. Stories about hidden technology and secret visitors have always found fertile ground whenever science hits an unexplained wall. The lore surrounding Roswell, government cover-ups, and high-ranking whistleblowers has shaped how we react to any cosmic mystery, even when the evidence is thin. In the case of 3IATLAS, these cultural undercurrents are bubbling up again. Some people are seeing patterns in the data and wondering if this is just another chapter in a much older, hidden story. Rumors are circulating, fueled by decades of speculation about recovered craft or classified encounters, but none of it adds up to proof. The scientific method demands solid, repeatable evidence, not just intriguing patterns or echoes from the past. For now, the only certainty is that 3IATLAS is raising questions that science can't yet answer. Until the data speaks for itself, every extraordinary claim remains just that, a claim, not a conclusion. The next wave of observations will matter more than any rumor or legend. December 19, 2025 is the date circled on every astronomer's calendar. It's the defining checkpoint for 3IDTLAS. On this day, the object will make its closest approach to Earth, at a distance of about 270 million kilometers. Around the world, telescopes are scheduled for continuous observation, from high-altitude observatories in Chile and Hawaii to orbital platforms like Hubble and the James Webb Space Telescope. Networks of amateur astronomers have coordinated campaigns to capture every possible detail. The data collected will go far beyond simple pictures. Teams are preparing to analyze the object's spectrum, the composition of its dust, its jet activity, and any changes in its trajectory with unprecedented precision. For months, speculation and debate have filled the void left by incomplete information. Now, the focus is shifting to what the evidence will actually show. Researchers and the public alike are calling for full transparency, raw data, real-time releases, and open peer review. December 19th isn't just another waypoint on a chart. It's the moment when conjecture gives way to measurable reality. The world will be watching, and the numbers will have to speak for themselves. Right now, space agencies worldwide are rewriting the rules of planetary defense, whether by necessity or by design. The line between scientific preparedness and military expansion is blurring with every new anomaly. As technology accelerates, so does the risk of decisions being made in secrecy. The sky no longer waits for us to reach a consensus. Are we ready for what happens when uncertainty becomes policy? Let me know what you think in the comments below. And if you want to follow this story as it unfolds, be sure to subscribe. Thanks for watching.